Hello and welcome to this video lesson on Changing Gas Equilibria. It has specification reference 3.1.10. And our lesson objectives for this video lesson are: what will the qualitative effects be of changing the temperature and pressure on the position of equilibrium? And what will be the qualitative effect on Kp of changing the temperature? And why hasn't pressure been included in that lesson objective? And lastly, how will catalysts affect the position of equilibrium and therefore Kp, which describes the position of equilibrium in a gas equilibria? Okay, there are three questions we want to answer in this video lesson. Let's start off with temperature. But first, a quick reminder of Le Chatelier's principle from last year. And here's a statement that describes Le Chatelier's principle. If a dynamic equilibrium is disturbed by change in the conditions, the position of equilibrium moves to counteract the change. So let's, for completeness, just unpick this statement. Dynamically equilibrium as opposed to a static equilibrium, i.e. there's two reactions, a forward and a backward reaction going on at the same time. Forward and backward reactions going on at the same time is disturbed by changing the conditions. Right, so what conditions do we mean? So we mean things like temperature and pressure. And if we're going to change those, we're going to increase the temperature or increase the pressure or vice versa. And then we want to consider the position of equilibrium. What does position of equilibrium mean? Well, that means the number of reactant particles versus the number of product particles at equilibrium. And when we say an equilibrium, position of equilibrium moves, well, that means that you're either going to get more reactants if the backward reaction has been favoured, or more products if the forward reaction has been favoured. Okay, so that's that. And counteracting the change. Okay, so all that means is that we're going to do the opposite of the change that you've made to it, or the system has experienced. So if, for example, the temperature has been increased, right, then the equilibrium, i.e. the forward reaction or the backward reaction, will counteract that change by trying to reduce that temperature. And the opposite is true with pressure. Well, the same rather is true with pressure. If pressure 2 is greater than pressure 1, then the number of reactant particles and product particles will change in order to decrease that temperature back to what it was, something similar to what it was before. Okay, so that's a very quick reminder of Le Chatelier's principle. Now we can go on to consider the effect of temperature on Kp. Okay, here's a bold statement about temperature and its effect on Kp. And we're saying that the change in the temperature of a system will change Kp. So let's consider an example. So let's consider the reaction between sulfur dioxide and oxygen. Right, and the balanced symbol equation is going to be 2 moles of sulfur dioxide gas plus a mole of oxygen gas. That's going to be in equilibrium with 2 moles of sulfur trioxide gas. And the delta H for that reaction is minus 197 kilojoules per mole. So what that means is that this forward reaction is exothermic and this backward reaction is endothermic by convention. And let's consider a numerical example to make this clear. let's consider a number of molecules. Let's say that at T1, let's put T1 here, at temperature 1, there happens to be at equilibrium 50 molecules of sulfur dioxide. Let's say there's 25 molecules of oxygen, and let's say there's 50 molecules of sulfur trioxide. And then what we do is we change the temperature. And let's say that temperature 2 is greater than temperature 1. So we've increased the temperature. And then, so what we want to do is we want to see what's going to happen. So the equilibrium is going to try and remove temperature from the system. And that's therefore you're going to get more endothermic reactions. And so that's the backward reaction. So what you might get is you might get at equilibrium, you might get only 40 of these sulfur trioxide molecules because a net 10 of them have decomposed back into sulfur dioxide and oxygen. And if the net 10 have decomposed, then you're going to get an extra 5 oxygen molecules, so that's going to be 30, and you're going to get an extra 10 sulfur dioxide molecules like that. And Kp, of course, is all about pressure. So let's consider the pressure or the partial pressures of each of these gases. So, of course, we've gone from 50 to 40. So the partial pressure of sulfur trioxide is, well, let me write that properly. Partial pressure has decreased. Whereas both of these changes have increased the number of molecules, and so the partial pressure of both of those has increased. Okay, so considering, because we've had more endothermic reactions going on. So let's now consider what effect those changes in partial pressure will have on Kp. So we have to remember that Kp is the partial pressure of sulfur trioxide, and that's going to be squared because we've got 2 moles there, divided by the partial pressure of sulfur dioxide, also squared from that 2 there, times partial pressure of oxygen, like that. And so what you can see from the workings is that our numerator has decreased and both of our denominators have increased. So the net effect of those 2 changes is that Kp at temperature 2 is going to be less than Kp at temperature 1. Or in words, if we increase the temperature where the forward reaction is exothermic, we're going to get a decrease in Kp. And if we decrease the temperature instead, for the sake of completeness, the opposite is going to happen. So why don't, for the sake of completeness, we go through on the same slide this situation where we decrease the temperature. So what we're saying is that instead of T2 being greater than T1, we're saying that T2 is less than T1, right, in which case Le Chatelier's principle is going to suggest we get more of the exothermic reaction going on at the expense of the endothermic reaction. So instead of 50 molecules of sulfur trioxide being produced, you might get 60 molecules instead. And to make those extra 10 molecules of sulfur trioxide, you're going to use up 10 molecules of your sulfur dioxide, so that's going to be 40 instead of 50. And you're also going to use up 5 molecules of your oxygen, so that's going to be 20 instead of 25. So with those changes happening, you can see that for sulfur trioxide on the right, the partial pressure has increased, and for the two reactants, instead of an increase in pressure, the partial pressures have decreased. And so the same Kp formula, instead of increasing the numerator, we've instead of decreasing our numerator, we have increased our numerator, and instead of increasing our denominator, we have decreased our denominator, in which case our Kp at the new lower temperature is going to be greater than our Kp at the previous higher temperature. So in summary, in words, if you decrease the temperature where the forward reaction is exothermic, you're going to get an increase in Kp. So now, considering the effect of changing the pressure on Kp, what we're saying here is that changing the pressure will not change Kp, which might be counterintuitive, but it's true, and let's work out why. By considering the same reaction, so we've got 2 moles of sulfur dioxide reacting with 1 mole of oxygen, and that's all in equilibrium with 2 moles of sulfur trioxide. So what you can see from this equilibrium is that on the reactant side there's 3 moles, but on the product side there's only 2 moles. So we have an imbalance in the number of moles, reactants versus products. So that means that a change in pressure can change the forward reaction versus the backward reaction. So let's consider that if we have increased the pressure, then what we want to do is we want to decrease, if we're increasing the pressure, we want to decrease the number of moles. So that means the forward reaction is going to proceed more at the expense of the backward reaction, and the corollary of that is that if our pressure is decreased, we're going to want to make more moles, in which case our backward reaction has increased at the expense of the forward reaction. Okay, so let's see the effect of that on Kp, because what we're saying is that despite these changes in forward reactions versus backward reactions, we're still saying that Kp is unchanged by changes in pressure. So Kp, if we remember, is the partial pressure of our product, all squared, over a partial product of our reactants, times each other. So that's our expression for Kp. So let's, in red, let's do an increase in pressure. So if we're increasing the pressure, then we have said that our forward reaction has increased, in which case our partial pressure of sulfur trioxide has increased. So if that was the only change, then Kp would change. But what happens simultaneously is that you've increased the pressure, so you've also increased the total pressure, including the pressure of your 2 reactants, SO2 and your oxygen. And these two changes counteract each other. They balance each other out. So the fact is that Kp at P2 is the same as Kp at P1. And let's just go through that also with a decrease in pressure. So at a decrease in pressure, what we've said is that the backward reaction is favoured because we want to make more moles. And if the backward reaction is favoured, then we're going to decrease the number of moles of sulfur trioxide, and therefore the partial pressure of sulfur trioxide. But as before, we've decreased the total pressure, and so that includes the partial pressures of sulfur dioxide and oxygen as well. So they have decreased. Right, and in the same way, these two decreases are of the same ratio, so they cancel each other out, and so Kp at pressure 2 is still equal to Kp at pressure 1 in the same case. So hopefully what you can see there is how that Kp is not changed even when you change the pressure, even for reactions where you've got a different number of particles on the reactant side versus the product side. So moving on to the effect of catalysts on Kp, what we're saying is that using a catalyst will not change Kp, just like it didn't change Kc when we were doing equilibrium in year 12. So let's write out our reaction again. 2 moles of sulfur dioxide plus a mole of oxygen in equilibrium with 2 moles of sulfur trioxide. Let's say we started off with just a bunch of sulfur dioxide molecules and a bunch of oxygen molecules in a container, and we left that container for enough time for equilibrium to be reached. So what would happen is that you'd get sulfur dioxide molecules reacting with oxygen molecules and making sulfur trioxide molecules, but then some of those sulfur trioxide molecules would decompose back into sulfur dioxide and oxygen, and at equilibrium the number of sulfur trioxide molecules formed by the forward reaction is the same as the number of sulfur trioxide molecules decomposed by the backward reaction. So let's draw a graph of that, where we might have our partial pressure of sulfur trioxide against time, and in red, let's draw our curve for the partial pressure of sulfur trioxide with no catalyst. Right, so it's 0 at the start, and at the start you got quite a lot of reactions, forward reactions happening, and they plateau off as the number of sulfur trioxide particles increase, and therefore the number of decomposing reactions also increases. So that's what we see there, and when that the time at which that plateaus out, let's call it this time here, let's call that T1, where T1 is time for equilibrium to be reached, EQBM reached without catalyst. Now let's say we do that whole same reaction with a catalyst, so what the big bold black statement at the top is saying is that we will not change Kp. Right, so the partial pressure of Kp at the end is going to be the same. So we're going to reach the same equilibrium position, like that. In which case the curve plateaus out about here, and let's call that T2, where T2 is the equilibrium reached with a catalyst. And what we can see is the equilibrium position is the same. So the equilibrium position has not changed, but the time for it to be reached has decreased. And that's because a catalyst will, let's write it down in fact. So the catalyst will increase the rate of both forward and backward reactions. Equally. So that means that the same equilibrium position is reached, but it's reached quicker. And that completes the video lesson on changing gas equilibria. Let's just check that we've covered off and answered our 3 questions. So what qualitative effects will change in the temperature and pressure have on the position of equilibrium? So changing the temperature does change Kp, and changing the pressure doesn't change Kp. And that answers the second question as well. And also we looked at catalysts just now. How will catalysts affect the position of equilibrium? And they don't affect the position of equilibrium, just the speed at which equilibrium is reached. Okay, so there's our lesson on changing gas equilibria. I hope that's been clear.